say electric potential due to continuous charged bodies. Children, this topic is a charged conducting sphere. What is meant by charged conducting sphere? Any charge is given to the sphere, it resides only on the outer surface. To find the potential at any point, we need to use the relation between electric potential and electric field. That was we have discussed in last class, dV equal to minus E bar dot dr. For that one, we need what is the electric field inside? 0. What is the electric field on surface? 1 by 4 pi epsilon naught q by r square. What is the electric field at outside? 1 by 4 pi epsilon naught q by r square. That means it's a sphere of charge which is having a charge of capital Q on its surface. Then we need to find potential. First, we will calculate the outside point. To find it, I will consider a point, some point randomly point as some A, and this is the O, which is at a distance R, where I would like to find potential at A. This is outside point, that is small r is greater than capital R. For that one, we need to use this relation. That's why I will take dV is equal to minus E bar dot dr bar. That means take integration on both sides. Integral dV is equal to minus integral E bar dot dr bar. Now we are bringing a charge from infinity to a point P, that's potential at infinity to potential at any distance r. And here r changes from infinity to some distance r. If we are integrating, integral of dV is V, and if we are applying limits, V of r minus V of infinity, potential at r to potential at infinity is equal to minus integral of infinity to r 1 by 4 pi epsilon naught capital Q by r square into dr. Then we will get V of r. That means we are assuming potential at infinity is how much? 0 is equal to minus Q by 4 pi epsilon naught is constant, and 1 by r square integration is minus 1 by r, infinity to r. Then we will get here as V of r is equal to minus Q by 4 pi epsilon naught minus 1 by small r minus plus 1 by infinity, which gives to you V of r equal to 1 by 4 pi epsilon naught capital Q by small r. This is the potential at a point which is outside. Now from this one, it's very, very easy. For on surface, what happens? Small r equal to capital R. That's why we are getting this relation. Now we have to come for the inside point. If you come for inside point, inside point means small r is less than capital R. Then according to the relation we have, dV is equal to minus E bar dot dr bar. That means integral dV is equal to minus integral of E dot dr. Then here V on surface to V inside point. That means if I consider a sphere and whose radius is r and charge is uniformly distributed over its surface, so that the potential on the surface is Vs, that is already we found as 1 by 4 pi epsilon naught q by capital R, and we would like to find at a point which is inside where it is Vin, which is at a distance of r. Then on integration, integral of dV means dV, that means V inside minus V on surface, which will be equal to minus integral of infinity to capital R to small r. E inside is E inside into dr. As we know that E inside is 0, therefore this term is 0. That means V inside minus V surface equal to 0. That's why V inside is equal to V surface. That means at inside point, the potential is 1 by 4 pi epsilon naught capital Q by capital R. This is very, very important result. Just previous topic we have discussed equipotential surface. Now here it's a surface of sphere. It's a sphere completely inside any point potential is same, so that the potential, the surface is, the total inside sphere is equipotential surface. That means if you are moving any charge from interior center to the surface, or you are bringing from r by 2 to r, what is the work done? Zero. Since equipotential, it's a surface of same potential. This is very, very important result. This is for conducting sphere. Now let's come for non-conducting sphere of this sphere, same thing. Now when we come across to non-conducting sphere, if I came for non-conducting sphere and charge is distributed uniformly over it with surface charge density or volume charge density as rho. If it is a non-conducting sphere, first we need to write the relations for electric field. What is the electric field of for outside point, which will be same as 1 by 4 pi epsilon naught capital Q by R square, where Q is capital Q is total charge. Now E on surface is 1 by 4 pi epsilon naught total charge on the sphere by surface. These two formulas are same as conducting sphere. Now for inside point, we have derived as 1 by 4 pi epsilon naught Q into small r by r cube. In the previous classes, we have derived. Previous classes, we have derived the expression as 1 by 4 pi epsilon naught Q r by r. Then, as we are deriving from previous relations, electric potential at outside point is same as the previous relation 1 by 4 pi epsilon naught Q by small r. It's not need to derive. It's same as the previous conducting sphere we have derived. V on surface is also same. 1 by 4 pi epsilon naught Q by capital R. There is a difference for inside. We need to derive now. Inside will not be same as for conducting. Now how to derive? Same relation. That means dV is equal to minus E bar dot dr bar. And dV is equal to integration V on surface to V inside dV is equal to minus 1 by 4 pi epsilon naught Q small r by r cube into dr. For inside, formula is 1 by 4 pi epsilon naught Q r by r cube. Then let's integrate. After integration, left side term is V inside minus V on surface is equal to minus Q by 4 pi epsilon naught r cube into r square by 2 integral of that one capital R to small r limits, and here integral of x dx is equal to x square by 2. Our general formula is integral of x power n dx is x power n plus 1 by n plus 1. Due to that reason, integral of r dr is r square by 2. Limits are capital R to small r. Now let's continue the further integration. Therefore, V inside is equal to minus capital Q by 4 pi epsilon naught r cube into, after substituting the limits, small r square by 2 minus capital R square by 2 plus V on surface. That is V inside is equal to, let's expand the terms, minus 1 by 4 pi epsilon naught Q r square by 2 capital R cube minus plus Q by 4 pi epsilon naught into Q r square by 2 into r cube plus V on surface is 1 by 4 pi epsilon naught Q by capital R. Here one thing is common, Q by 4 pi epsilon naught is common. Then we will get r square by 2 capital R cube plus here it is 1 by 2r, it is 1 by r. Here it is minus. Then in the next step, we'll get as P inside is equal to minus, if I take common, minus q by 4 pi epsilon naught, or if I also take common, we will get this expression as small r square by 2 capital R square, that is minus already taken, 2 is there, then small r square by 2 capital R square plus 3 by 2 is the answer for electric potential at inside point. Hello, a small correction. As we're taking minus as common outside, here we will get minus 3 by 2. At the center of the shell, at the center of the sphere, at the center of the sphere, small r equal to 0. That's why electric potential at center is minus 1 by 4 pi epsilon naught into 3 by 2 times of q by r. Otherwise, we can say minus 3 by 2 times of potential on surface. Minus 3 by 2 times of potential on surface. Do you clear? Sorry, it's plus. Okay, plus 3 by 2. Plus 3 by 2 times of potential on surface for positive charge. For negative charge, it will come as a negative. Now, let's draw a graph for conducting as well as non-conducting sphere. If you draw a graph between potential versus distance, as we know that potential at inside point is same, which will be equal to on its surface. That means up to small r equal to capital R, it's a constant. Later on, it will change as rectangular hyperbola. That is V proportional to R. Now, if you take for, this is for conducting. If you consider for non-conducting sphere, then if you're considering distance on x-axis and potential on y-axis, the graph will be like this. Initially at inside point, potential was there. Until then, it will be a parabolic graph. Potential on surface here, and it is small r equal to capital R. Later on, it is a rectangular hyperbola. Since V proportional to 1 by R. This is the graph between conducting and for a graph for non-conducting and non-conducting spheres in case of spherical bodies. Similarly, we can derive for cylindrical and wire and everything. If they ask, you have to follow the relation dV equal to minus E bar dot dr. For NCERT level, only the spheres are sufficient. Wherever it's required, try to derive them by using the relation by similar method. Thank you for this.